Okay, today I shall speak about a few issues regarding superstrings. First we will look at how to compute the string propagator. This plays a fundamental role in calculating amplitudes for scatterings of for interaction between strings. So, in the case of, we will consider the bosonic string. So, the action is given by, S is given by integral, I am taking flat space time over the d-dimensional space time, but the worldsheet can have a metric. So, it is given by h alpha beta root minus h, then dou alpha x mu dou beta x mu d2 sigma. This root minus h is included. So, it becomes a tensor h alpha beta x mu dou alpha x mu dou beta x mu, that becomes a scalar, and root minus h d2 sigma is an invariant. That is, if you change the coordinates h dash d2 sigma dash, if you apply a diffeomorphism of the coordinates, space time coordinates, then this is the invariant area measure on the string surface. From general relativity we know that this is an invariant, and we want to compute, the aim is to compute path integrals. So, when you discuss scattering of strings, we take the action like this and then you integrate dx, but you also, the action also depends on the worldsheet metric. So, you also have to calculate dh, things like this. For example, when you have a function of the metric end of the string, functional of the metric end of the string, you want to calculate its average value, then you will insert that here and you will calculate the average value. So, as you do in conventional quantum field theory. Now, to compute such a compute this path integral, you are integrating over h and also over x, and what is s of hx? S of hx is given by half integral eta alpha beta, or you are taking a curved metric, right. So, h alpha beta, which is a function of tau and sigma, and root minus h and dou alpha x mu dou beta x mu d2 sigma. So, h is a 2 cross 2 matrix valued function, 2 cross 2 matrix valued functions of function of tau and sigma. So, by using reparametrization invariants and while scalings, you can also, that is by using conformal transformations in which h alpha beta of tau sigma is mapped to e power phi times phi of tau sigma, where phi some scalar into h alpha beta tau sigma, and reparametrizations. Which means nothing but diffeomorphisms of the space time manifold, string space time, string worldsheet coordinates tau dash sigma dash, diffeomorphisms. You can always bring the metric h to the standard form h alpha beta by using these two transformations, conformal transformations as well as reparametrizations. You can bring it to the form 0 1 1 0. If you do not use conformal transformations and only use reparametrizations, then you can bring it to the form e power phi times 0 1 1 0, where phi is an arbitrary function of tau and phi some function of tau and sigma. So, we start with this metric and then you apply a reparametrization. You start with, let us say, h0 of phi, which is given by e power phi 0 1 1 0, and then you apply reparametrizations. Let us say where sigma plus which is tau plus sigma, and sigma minus which is tau minus sigma. In this system of coordinates, if you use this metric, then it becomes it gives you the worldsheet metric in terms of sigma. That is, if phi were for example 0, there were no conformal transformations, then the metric would simply be d sigma plus d sigma minus, which is d tau square minus d sigma square, which is flat space time. If you have a conformal factor there here, then it will become e power phi times d tau square minus d sigma square. Now, by applying reparametrizations, so let us say you take let us say your metric is h, you start with some metric h and you apply a reparametrization, then what will h change to? H alpha beta will change by the killing form. So, it will go to you can write it as del alpha xi beta plus del beta xi alpha from a well known theorem in general relativity. It is based on using the fact that if you take an infinitesimal transformation, so that sigma alpha goes to sigma alpha plus xi alpha of tau sigma, or tau alpha tau let us say tau of sigma. Sigma means it's a vector, tau and sigma, or sigma 0 and sigma 1. Sigma 0 is tau and sigma 1 is sigma. So if you make this transformation, the metric transformation will be h dash alpha dash beta dash of tau dash sigma dash, that means of sigma dash, that is equal to, let us consider the covariant transformation. So h alpha beta, h dash alpha dash beta dash of tau dash sigma dash or of sigma dash is equal to h alpha beta of tau sigma into dou sigma alpha by dou sigma dash alpha dash into dou sigma beta by dou sigma dash beta dash, where you can compute, for example, if I call this as sigma dash, sigma alpha dash, sigma dash alpha dash. So you have that the relation that dou sigma alpha by dou sigma dash alpha dash is equal to delta alpha alpha dash plus, or there will be a minus sign because this is a first order term, first order smallest term. So up to first order this will be dou xi alpha by dou dou sigma alpha dash, dou sigma alpha dash. So by using this in this formula and omitting second order of smallest terms, you can show that the metric will change by xi alpha is a function of sigma, so you are differentiating with respect to sigma dash. So yeah, you can show that the metric will change by delta h alpha beta under an infinitesimal reparameterization. It will change by del alpha xi beta plus del beta xi alpha, where del alpha is the covariant derivative taken with respect to the metric h, right, the current metric from where you are deviating. And if you use the light cone coordinates, then you can write this in the form delta h plus plus is equal to del plus xi plus delta h minus is equal to 2 del minus xi minus, and delta h plus minus is equal to del plus xi minus plus del minus xi plus. So if you compute, if you reparameter, the reparameterization group is denoted by G, which consists of all reparameterizations, all functions, all pairs of functions of the worldsheet coordinates xi plus and xi minus. They are functions of sigma plus and sigma minus, or equivalently of tau and sigma. So the group consists of all such reparameterizations, and when you start with, let us say I start with a metric h0 which is e power phi 0 1 1 0, then what happens is that your metric, when you say hg, that means how much does h change by g. If you look at this, so if you transform h by g, that means I apply the system of, I apply a reparameterization xi plus xi minus and see how h changes by. For an infinitesimal g, that is when xi plus and xi minus are infinitesimal, I know how it changes, as I just saw. So now this denotes the change metric. Now you use the fact that if you so I look at h plus plus, I consider the equation delta h plus plus delta h minus minus, this is called gauge fixing, into dh plus plus, a path integral dh minus minus, this integral is 1, okay, from basic proper definitions of the delta functional. Now if I change, I can write this in the following way, since h plus plus h minus minus are just two coordinates, they can be viewed as two coordinates. So you can start from one h plus plus h minus minus and go by a reparameterization group g element to hg plus plus hg minus minus, and it will cover all the h plus plus h minus minus, okay, it will cover all of them by as g, because g is a 2 parameter group, it depends, it is parameterized by xi plus xi minus, and h plus plus h minus is 2 it's also a 2 parameter. So if I start with a metric which has which is of the form say e power phi times 0 1 1 0, I can arrive by using reparameterization at any other worldsheet metric by adjusting phi appropriately. So I fixed a phi, so I can write this equation as, if I look at dh plus plus, this differential of the path integral, this can be written as the Jacobian dh plus plus divided by dg or xi plus, it depends only on xi plus, determinant of this, likewise into d xi plus, because it depends only delta h plus plus, delta h plus plus is given by del plus xi plus, likewise delta h minus minus is del minus h minus, so it will depend only on xi minus. So I can write this equation equivalently as integral delta h plus plus delta h minus minus into the determinant. So determinant of d h plus plus, so I make a transformation by g and then I take dg by d xi plus into determinant of d h plus plus g by d h xi minus, and then I say dg. When I say dg, it means d xi plus, means d xi plus d xi minus. So this is, it is a path integral. So you say, you write capital D here, dg is capital dh plus xi plus plus d xi xi minus. So this is 1. So by making a change of variables, I can write the delta function identity in this form. So what is delta, what is this determinant? This determinant is equivalently, you can say that this determinant d of hg by d xi plus plus, that is equal to determinant of delta plus evaluated at hg, okay, it is evaluated at hg, likewise d of hg by d of hg plus plus, this determinant, likewise d of hg minus minus by d xi minus, do not put a double plus here, d xi minus, this determinant is nothing but determinant of del hg minus, evaluated at this. So what I can, so I get the equation delta h plus plus g delta h minus minus g into determinant of del plus at hg into determinant of del minus at hg g, and then dg, that means d xi plus plus d xi minus minus, this is 1. So I insert this identity into the string path integral in which the metric has not been integrated. So what do I get? I get that the same path integral, namely s, I consider half, this is nothing but half h alpha beta root minus h dou alpha x mu dou beta x mu d2 sigma, this is s is a function of h and x. So I consider e power I s hx dx, I consider this path integral without integrating over the metric, and I substitute that one equation, that identity into this, and then I integrate over h, right, I can substitute that. So I want to compute basically this path integral. So this is equal to integral e power I s hx, then I substitute for that, that will give you delta h plus plus g, delta h minus minus g, and then I put determinant of del plus at hg, determinant of del minus del minus at hg, and then I put dg, this is 1, and then I integrate with respect to h and x both. So I integrate with respect to x followed by an integration with respect to h. Since this is simply a one factor, the integral over of this quantity with respect to g is 1, I can insert this 1 and write it in this way. Now I make a change of variables, that means I use, instead of using hg and g as the integration, instead of using h and g, so here dg, and you are integrating over h also. So instead of using so your d, okay, instead of using h and g as the integration variable, I use hg and g as the integration variable. So I call hg as h dash, okay. Then what happens is that this integral becomes integral e power I times s of, then hg inverse it will become, comma x, okay, and it will become determinant of, so hg I am calling as h dash, hg I am calling as h dash, so h becomes h dash g inverse, so h becomes h dash transformed by g inverse. So it becomes like this, and then determinant of h delta plus at h dash, determinant of del minus at h dash, and then I integrate with respect to x, I integrate with respect to h dash, okay, I integrate with respect to h dash and I integrate with respect to g. So, the path integral becomes this, and of course, you also have a delta function attached to this. You have those delta functions, delta of h plus plus dash, delta of h minus minus dash. H plus plus dash is h plus plus g transformed by g, h minus minus dash is h minus minus transformed by g. So, if I now integrate this over h dash, if I now integrate this over h dash, what do I get? H dash, how is h dash specified? H dash is specified by specifying h plus plus dash, h minus minus dash and phi, which is the conformal factor. H dash is specified by specifying this. So, if I integrate over h plus plus dash h minus and d and g consists of dg involves integrating only with respect to h plus plus, sorry, with respect to xi plus xi minus, okay. H plus plus dash consists of these three integrations. If I integrate, if I write dh dash as d h plus plus dash, d h minus minus dash and dg, and then I integrate over the delta function, that amounts to substituting h plus plus dash and h minus minus dash equal to 0. So, this will be simply equal to integral e power I times s of when you put h plus plus dash is 0 and h minus minus dash is 0, that means that the metric, what does h dash become at that point? H dash metric at that point becomes simply e power phi times 0 1 0 1 1 0, which is a standard metric. I call it as h0 of phi. When I put h plus plus dash and h minus minus dash equal to 0 corresponds to this sort of a metric. So, I will call that as h0 phi, h0 phi, and transformed by g inverse, right, transformed by g inverse. It means transformed by g inverse comma x, and then here you will have determinant of delta plus evaluated at h dash equal to 0, that means evaluated at this metric h0 phi, evaluated at h0 phi. So, let us call this metric, give it a name, let us call this metric as h0 phi transformed by g inverse. Let us call this as something like h1 of phi, okay. So, this h1 of phi is obtained, this h1 of phi is obtained by and then you are following it by g via reparameterization element. So, you are applying a transformation to this metric, you are applying a reparameterization transformation to the metric e power phi 0 1 1 0. That means you are applying a you are looking at h0 phi g inverse corresponds to the change in h0 phi under a diffeomorphism of the worldsheet space time coordinates g inverse. So, this will become simply let us call this as h0, let us call this as h, okay, let us give it not call it by anything, let us just retain this h0 phi g inverse, okay, determinant h plus h delta plus and then determinant del minus. When h dash has become 0, when h dash is 0, it corresponds to this metric, and then you have dx and dh plus, in dh dash I have integrated over h plus plus dash, I have integrated over h minus minus dash. So, it remains to only integrate over phi and then dg. Now, you see what is happening here is that when you change the metric by this, by a diffeomorphism, then what happens to the action? What happens to the action? Suppose I change, suppose I start with a metric h alpha beta root minus h, then you are saying x mu comma alpha, x mu comma beta d2 sigma, and suppose this is the action, suppose I change my h by a diffeomorphism, then what happens? Suppose I change h by a diffeomorphism, that means by a reparameterization, then h will change to so what will h change to? If you change it, if you look at the, let us call the diffeomorphism as sigma dash is equal to T of sigma. So, suppose I compute h dash at alpha beta at sigma dash, suppose I look at this quantity, or suppose I look at the contravariant version of this h dash of alpha dash beta dash at sigma dash, okay. I can write this and also I am changing this root h dash minus h dash at sigma dash. So, I am changing this by this thing, I am changing this metric to this thing, and I am also, and I am changing the, I am calling sigma as sigma dash. So, I call it as h mu comma alpha, but now evaluated at, so let us keep it as it is, let us call the h alpha beta, let us call this h alpha beta. So, x mu at alpha at sigma dash, x mu at beta at sigma dash, d2 sigma dash. I can also write it in this form, the same integral with when h has been changed by g. So, this is changed by some g here, h g equal to h dash. Okay, change by reparameterization. That means first I apply the standard change in the change of transformation of a tensor formula and replace your sigma dash by T inverse sigma dash, T inverse sigma. That means I replace by T inverse sigma dash, I replace it by, so that I evaluate it at sigma. So, this is going to change by what? This h dash at alpha beta at sigma dash, this is nothing but h rho let us say h a b at sigma into dou T alpha sigma by dou sigma a dou T beta sigma by dou sigma b, right. So, it is this is the change of variable formula for the metric. So, I apply this change, root h dash sigma dash into d2 sigma dash is same as root minus h sigma into d2 sigma, because it is the invariant area element. So, this will change it this way. So, what will change is that x mu at alpha, you are differentiating x mu at alpha. What is this term? This term will become dou x mu by dou x alpha. Dou x alpha means it is this, you are differentiating with respect to sigma alpha dash. So, it is dou T alpha at sigma, and then you also have so this evaluated at sigma dash, and similarly you have dou x mu. So, dou x mu sigma dash by dou T beta sigma multiplied by this term which I have here. So, that will be dou T alpha sigma by dou sigma a into dou T beta sigma by dou sigma b. So, you can apply the chain rule and this will cancel out. We are first, so this the product of these these four terms is simply dou x mu at sigma dash, but now differentiated with respect to sigma a, and similarly dou x mu sigma dash divided by dou sigma b, where sigma dash is T of sigma, So, in other words, what I can say is that if I make a transformation SHG at x, this quantity, this is nothing but SH at you are replacing it by T of sigma. So, let us call it as x of t, where x of t means x of t evaluated at sigma is equal to x of t of sigma. So, in other words, if under this transformation, what will happen to the path integral? It will become e power I s h of g inverse comma x into dx into dg into d phi, okay, where your h is given by h0 of phi, which is equal to e power phi 0 1 1 0, and we have seen that this quantity can be written as e power I times s of h of x of t into dx into dg into d phi. So, d phi decouples, h is equal to h0 phi, h is h0 phi. So, that will decouple, it will integrate out, and it amounts to replay, and it amounts to using simply the flat spacetime metric h0, right. H0 is the flat spacetime metric, which is 0 1 0 1 0. This is called gauge fixing. By integrating out, by introducing a delta function factor and then integrating over the metric, I am able to gauge fix. I can assume without loss of generality in computation of path integrals that this h0 is nothing but the standard flat spacetime metric for the world sheet, because integration over g is not going to give anything, it will just give a constant. You can remove this as well. So, you are left just with this sort of a path integral. Having done this, we are in a position to say that the total action can be written as the total path integral e power I s h x dh dx. This can also be written as integral e power I s with the standard metric h0x, where h0 is flat space time metric 0 1 1 0 multiplied by determinant of del plus, okay, determinant of del minus, and then dh dx, where h0 is simply this metric, and I can write determinant del plus, I can write in the form of a Berezin integral. Determinant of del plus can be written as integral e power integral, I call it as c plus sigma, okay, c plus sigma del plus b plus sigma d2 sigma and then dc plus db plus. It is a Berezin integral where c plus and b plus are functions of only sigma plus, because del plus depends only on sigma plus, right. So, and likewise I can replace determinant of del minus by integral e power integral c minus sigma del minus into b minus sigma d2 sigma dc minus db minus. So, in other words, the path integral amount, calculating the path integral after gauge fixing amounts to simply replacing, simply adding two additional terms to the Lagrangian, namely this term and this term. So, the new gauge fixed action after adding, these are called Faddeev-Popov-Gauss, these are called Faddeev-Popov-Gauss, right. The fields C plus sigma, B plus sigma, C minus sigma, B minus sigma, these are called ghosts, because they are fictitious variables introduced to take into account whenever gauge fixing is done, whenever you adopt a particular gauge and the gauge fixing is justified, that is the path integral does not depend on what gauge you are choosing, that we just proved by using by introducing the delta function, delta functional of the metric tensor of the world sheet. So, these are called Faddeev-Popov-Gauss, it amounts to replacing the bosonic action. So, the bosonic fraction becomes now S of h, h0 x, let us remove h0, h0 corresponds to simply the flat space-time metric. So, it is S of x, the bosonic action, plus integral c plus sigma dou plus b plus sigma plus c minus sigma dou minus b minus sigma d2 sigma. You can use this because the covariant derivative with respect to the metric 0 1 1 0 is simply dou plus, del plus becomes simply dou plus and del minus becomes dou minus, where Sx is the bosonic action. So, these are additional fermionic fields, C plus sigma and C B plus sigma and C minus sigma and B minus sigma, these are fermionic fields, they are called ghosts. What is the equation now? The equation of motion, by taking the variation with respect to C plus sigma, C minus sigma and so on, you get the ghost equations are dou minus of C plus sigma equal to dou minus of C minus B plus sigma, this is 0, and dou plus of C minus sigma is equal to dou plus of B plus sigma, B minus sigma equal to 0, which is nothing but the statement that C plus sigma depends only on sigma plus, B plus sigma depends only on sigma plus, C minus sigma depends only on sigma minus and B minus sigma depends only on sigma minus. So, these are the ghost equations. So, you can now introduce, so when you have a Lagrangian, suppose you take the plus part of the ghost, for example, say let us say I consider the ghost to be equal to only the plus part of the ghost. So, that is equal to C plus sigma dou minus B plus sigma. So, what is the canonical momentum corresponding to this? Dou Lg plus by dou tau B plus, right, that is the momentum which is equal to C plus sigma, because dou minus is nothing but dou tau minus dou sigma. So, differentiating with respect to dou tau sigma will give you this. So, what are the canonical anti-commutation relations? If you use the momentum, so this is the canonical momentum, C plus sigma is the canonical momentum field corresponding to the position field B plus. So, you will have B plus at equal time commutation relations, tau sigma comma C plus at tau sigma dash, this anti-commutator is equal to delta sigma minus sigma dash, and likewise for the minus part. So it should be actually sigma plus minus sigma plus dash, because it depends only on sigma plus. So at equal time you are calculating tau minus sigma becomes tau minus sigma is sorry, tau plus sigma is sigma plus and tau minus sigma is sigma minus. So sigma plus and you are taking at the same time, right. So tau plus sigma dash is equal to sigma plus dash and tau minus sigma dash is equal to sigma minus dash. So that sigma plus minus sigma plus dash is simply equal to sigma minus sigma dash. So it is a function of sigma plus and minus sigma plus dash, and likewise for the negative part. So you get the anti-commutation relation. Now we want to calculate the ghost energy momentum tensor, ghost energy momentum tensor components. So you know that in a basic in field theory what happens, if you have a set of fields phi k, let us say phi k comma mu, suppose this is the total action, and suppose you look at dou by dou x mu of this, dou by dou x nu of this can be written as dou L by dou phi k comma mu nu plus dou L by dou phi k comma mu nu summed over the repeated index. Use the equations of motion to write dou L by dou phi k as dou nu or dou nu of dou L by dou phi k comma nu into phi k comma nu, or let us write it as phi k comma mu, let us write it as, okay. So phi k comma mu dou mu of this into phi k comma nu plus dou L by dou phi k comma mu into phi k comma mu nu, right. By using the equations of motion for the field I am able to write it in this form, and this can be written as dou mu of dou L by dou phi k comma so dou mu of this, no, I have just first okay, just let me repeat it. You have L which is a function of phi k and phi k comma mu. So I calculate dou nu of L which is equal to dou L by dou phi k comma nu plus dou L by dou phi k comma mu into phi k comma mu nu. Replace this with the equations of motion. So this becomes dou mu of dou L by dou phi k comma mu summed over mu into phi k comma nu plus dou L by dou phi k comma mu nu, which is nothing but dou mu of dou L by dou phi k comma mu into phi k comma nu, right, by using the product rule for partial derivatives. First differentiate this with respect to mu, keep this fixed, then keep this fixed and differentiate this with respect to mu, you get this. So in other words, this equation can also be written as dou nu of, or you can write it as dou mu of dou L by dou phi k comma mu into phi k comma nu minus L delta mu nu. This is 0. So this is the energy momentum conservation equation, namely del by del mu of T mu nu equal to 0. So you identify this as the energy momentum tensor. You can show that in accordance with Noether's theorem, this corresponds to a symmetry around the symmetry of the Lagrangian under space-time translations, because the Lagrangian does not explicitly depend on the space-time arguments. That is why this conservation holds good. More generally in the case of suppose you have a Lagrangian like this which depends on the fields phi k and their first order partial derivatives, and suppose under a transformation, let us say phi k of x go an infinitesimal transformation, this goes to phi k of x plus epsilon is a small parameter, and then you have some fk of phi, fk of let us say it is a function of x tx and also of phi k at the same at a given time point t. It does not so phi k x means t and r, so at a given t and r dash, as r dash varies over all r. Suppose it is an infinitesimal transformation, which under which this Lagrangian remains invariant. That means you could have a group of transformations of the position field space under which this Lagrangian remains invariant. If you look at the generator of this group of transformations, diffeomorphisms over the functions over the field space, suppose the Lagrangian is invariant, then delta L is 0, which is equal to dou L by dou phi k into epsilon fk plus dou L by dou phi k comma mu. Phi k comma mu will change by how much? Epsilon fk comma mu, right, this is 0. Now I substitute for the equations of motion. Dou L by dou phi k can be written as dou mu of dou L by dou phi k comma mu, right, into epsilon phi k plus dou L by dou phi k comma mu into fk comma mu, right. This is 0, the Lagrangian is invariant. This equation can also be written as dou mu of dou L by dou phi k comma mu multiplied by fk. This is 0. That means you have a conserved quantity. The divergence of this is 0. This is called the Noether current. This is called the Noether current associated with this symmetry. So corresponding to this symmetry, infinitesimal set of transformations, or corresponding to this group of transformations of the field space which leave the Lagrangian invariant, I have a conserved current. Its divergence is 0. So you can write this as dou mu j mu is 0, where j mu is the conserved current. So j mu is the Noether current, which is equal to dou L by dou phi k comma mu into fk of fk of x comma phi. Now if you apply this to if you apply this relation, so you calculate the energy momentum tensor of the gauss field. You have the gauss field is given by Lg plus is given by C plus of sigma into dou minus of B plus sigma. So what is dou Lg plus by dou minus B plus, that is C plus. So you get immediately that in the light cone coordinate system you are, and delta plus minus is 0, delta plus minus is 0, delta minus plus is 0, delta plus plus is 1, delta minus minus is 1. So I get that the energy momentum tensor of this is, if I look at the T minus, if I look at the T plus plus component, that is equal to, what is the T plus plus component, tell me? T plus plus is given by dou L by dou L ghost by dou plus, so the Lagrangian is given by C plus dou minus B plus C minus dou plus B minus. So if you calculate dou plus B minus, so this multiplied by dou plus B minus, that depends, that is the only term which depends on dou plus, or on dou contains dou plus derivative. So if you look at this, what does this come out to be? This comes out to be equal to dou B plus, which is equal to C minus dou plus B minus. But when the equations of motion hold, dou plus B minus is 0, so this becomes 0. So this is equivalent to saying that T plus T minus plus is 0. Of course there is also a minus L delta plus plus, right, you have to say minus L delta plus plus is 1. So you have this minus L, but what is L? L is also 0 when the equations of motion hold good, because L is nothing but this quantity, and dou minus B plus vanishes, dou plus B minus vanishes. So T plus plus vanishes, which is equivalent to saying that T minus plus is 0, and T plus minus likewise is also 0 for the ghost fields. So it tells you that what is, how do you calculate, for example, T plus minus? You are using the metric 0 1 1 0. That means H plus minus is 1, H minus plus is 1, and H plus plus H minus minus are 0. So this is nothing but T minus minus H plus minus, which is 1, and that is all. And similarly T minus plus is nothing but H minus plus into H plus plus, and H plus minus is 1, sorry, T into this multiplied by T plus plus. this multiplied by H minus plus multiplied by T plus plus. So, H minus plus is 1 and this is T plus. So, this is nothing but T plus plus. So, T minus plus and T plus minus are 0, which means that these terms are 0, that means the trace of the energy momentum tensor of the ghost field is 0. Likewise, the trace of the energy momentum tensor of the bosonic field is also 0, because the bosonic string Lagrangian can be written as half dou plus x dot dou minus x. So, if you calculate for example T plus plus, which is same as T minus plus, which is same as T plus minus, if you calculate this, what will you get? You will get dou LB by dou plus x dot dou plus x, okay, minus L, and dou L by dou plus x will give you half dou minus x. So, it will give you same as dou plus x dou minus x minus L, which is 0 because L is same as this. So, the trace of this energy momentum tensor also vanishes, this component of the energy momentum tensor also vanishes, which means that at the classical level, when the equations of motion hold good, the energy momentum tensor is traceless in the classical situation. In the quantum situation, we will see that anomalies occur, that is it can acquire a finite trace when it interacts with gravity. But if you look at for example T plus plus and T minus minus, they are not 0, this is equal to T minus plus and this is T plus minus, they will not come out to be 0, both for the ghost field as well as for the bosonic field. So, if you compute for example T plus minus, this is nothing but dou L bosonic by dou minus x dot dou plus x dou minus x minus L delta minus plus is 0 because minus and plus are different. So, this is nothing but half dou plus x dou plus x. Since x can be written as a sum of a right mover and a left mover, this is equal to saying that this is the same as, and the right movers satisfy the equation dou plus x minus is 0 and the left movers satisfy the equation dou minus x plus is 0. So, this is the same as dou plus x plus dot dou plus x plus, right. So, this is non-zero, this means the only non-zero components of the energy momentum tensor in the ghost of the only non-zero components of the energy momentum tensor are T plus plus and T minus minus, T plus minus is 0. What happens in the case of ghost? In the case of ghost, if you look at the ghost Lagrangian Lg, this is nothing but C plus dou minus B plus C minus dou plus B minus, and if you compute the energy momentum tensor of this is nothing but T plus minus. We have seen already that T plus minus is equal to T minus plus equal to 0. No, sorry, T plus plus and T minus minus are 0. This is same as T minus plus and this is same as T plus minus, right. How did we see it? You just compute, for example T plus plus is dou Lg by dou plus B minus, that is the only term containing dou plus, and here you put dou plus B minus, and dou plus B minus vanishes when the equations of motion hold good. You put minus L, delta plus minus L also vanishes, the ghost Lagrangian also vanishes when the equations of motion hold good. So, the ghost energy momentum tensor is also traceless. What happens to T plus plus of the ghost? That is nothing but this same as T minus plus of the ghost. So, this same as dou Lg by dou minus x multiplied by dou plus x. Oh sorry, I should not put this, I should put dou minus of B plus and dou plus of B plus, okay. So, dou Lg of dou minus B plus is nothing but C plus. So, this is C plus into dou plus B plus, which is non-zero, right. Likewise, if you calculate T minus minus G, that will give you C minus dou minus B minus, which is non-zero. So, now you can calculate now, okay. Now, we want to look at anomalies. How are anomalies generated? Anomalies are generated in the following way. Suppose you look at the energy momentum tensor, okay, say T plus plus of sigma and you calculate the correlation T plus plus of sigma dash, you look at this quantity and time order version of this and you take vacuum expected values of this, take vacuum expected values of this and you see that you, in the case of let us say in the bosonics, you can see that T plus plus will satisfy the equation, this is equal to 0 by virtue, for example if you take the bosonic string, what is T plus plus, this is nothing but dou plus x plus into dou plus x into dou plus x is what is T plus plus apart from a scalar factor of half. So if you take dou minus of this, what will you get? You will get dou minus dou plus x into dou plus x into 2, which is 0 because dou minus dou plus is the wave operator in 2 dimensions, this is dou tau square minus dou sigma square and the string satisfies the wave equation. So this will vanish, right. So you suppose you try to compute now this quantity. So the energy, this says that the energy momentum tensor is conserved. This also happens in the case of ghosts, because in the case of ghosts what you have is Tg plus plus is nothing but C plus dou plus B plus, and if you take dou minus of this you will get dou minus of this into this plus C plus dou minus dou plus B plus, and dou minus of B plus is 0 and dou minus of C plus is also 0. So the ghost energy momentum tensor is also conserved. But what will happen is we will see that when it interacts with gravity and you take the quantum expected values, then this conservation law is also violated. So these are anomalies. So how do we compute them? For example, you look at T plus plus at tau sigma and T plus plus at tau dash sigma dash, and you take the time order version of this and take the vacuum expected value of this. What is this equal to? This is the vacuum expected value of theta tau minus tau dash into T plus plus of tau sigma into T plus plus of tau dash sigma dash plus theta tau dash minus tau into T plus plus of tau dash sigma dash into T plus plus of tau sigma. So if you differentiate this with respect to tau, suppose I call it as delta tau sigma tau dash sigma dash, I give this a name. If I differentiate this with respect to tau, what do I get? A differential of the unit sum function is a delta function. So this will give you a delta tau minus tau dash, and then I will differentiate this. So I will get something like, if I take dou tau of this, dou tau of delta tau sigma tau dash sigma dash, that will give you delta tau minus tau dash. Then here if you differentiate this with respect to tau, you get minus delta tau minus tau dash. So you will get a commutator here. It will be a commutator between T plus plus at, because of the delta function I can replace tau dash by tau here. So it is the equal time commutator of this T plus plus tau sigma dash, like this. And then you will have a differential theta tau minus tau dash into the differential of tau here, right, tau minus tau dash. Differential of tau is taken within the bracket, within the quantum expected value. So it will come out to be this. Similarly, when I calculate del sigma of delta, then it will act only on the inner variables. So I will get an equation of the form this plus theta tau minus tau dash into dou plus into dou tau of this and then dou minus of this. So I will get the equation as, I will get dou tau of delta tau sigma tau dash sigma dash is equal to delta tau minus tau dash times the vacuum expected value of tau plus plus tau sigma comma T plus plus of tau dash tau sigma dash plus I will get theta tau minus tau dash times, of course, the vacuum expected value of this into the vacuum expected value of dou tau minus dou sigma, which is dou minus of T plus plus tau sigma so likewise for the other theta function, so it will be simply the vacuum expected value of the time order version of this multiplied by T plus plus at tau sigma dash, right. That is because you will get a term like theta tau minus tau dash times vacuum expected value of T, it will not be vacuum expected value, it will be simply dou minus of T plus plus at this point and t plus plus at the second point, minus theta plus theta tau dash minus tau times the same thing, which will be dou, but now with the opposite, that is when tau dash is greater than t, it will act on this term will appear to the right into tau plus plus dash into dou minus tau plus plus. So if I combine these two, I can write it in this form, and by the equations of motion, dou minus of t plus plus is 0, the energy momentum tensor is conserved, so this is 0, so you get just this term surviving. So it means that whenever and this is nothing but the anomalous part of the commutator, you can see that, because when this quantity is non-zero, if the left hand side is non-zero, so also will be the right hand side quantity, and it will be a scalar which tells you the anomaly in the commutation relations between the energy momentum tensor, which when you translate to the Fourier series domain, it becomes an anomaly in the commutator of the Virasoro elements, Virasoro Fourier components, that is of the Fourier series components of t plus plus. So you can calculate the anomaly in this in the Virasoro commutation relations, namely the central charges, by simply calculating the correlations in the energy momentum tensor. Let us see how that is done. By Wick's theorem, you have to calculate tau sigma tau dash sigma dash. This is nothing but the vacuum expected value of t plus plus at tau sigma into t plus plus at tau dash sigma dash, right, into this. Now this tau plus plus, when you look at, let us say, the bosonic string, let us call the bosonic string as phi, or let us call it as simply as x. So t plus plus is nothing but dou plus of x into dou plus of x. Okay. So you are calculating the product of this evaluated at tau sigma multiplied by dou plus of x evaluated at tau dash sigma dash. Then you are taking the vacuum expected value after taking the time ordered version of this. By Wick's theorem, these are all expressible. X is expressible as a superposition of bosonic creation and annihilation operators. So you can calculate this by calculating the pairwise correlation of these 4 terms, pairwise correlation of these 4 terms, multiplying them and adding all of them up. So you will get terms like dou plus of x tau sigma multiplied by dou plus as x tau dash sigma dash plus the same term coming from by pairing. No, this will come by pairing this, and this second term will come by pairing this term and this term. So you are calculating the vacuum expected value of this and then whole square. But you already know, as we will soon see, that the bosonic string propagator is given by T of x mu tau sigma multiplied by x nu tau dash sigma dash, vacuum expected value is given by eta mu nu times log of mod sigma, you can say, or log of root of tau minus tau dash square plus sigma minus sigma dash square minus. That is because okay, this is the propagator. That is because of the following reason. If you look at this propagator, you try to apply, you also have you have a commutation relation of the form equal time commutation relation for the bosonic case of the form tau x tau sigma dash is equal to I times delta sigma minus sigma dash. So if you want to compute the propagators, let us say x tau sigma multiplied by x tau dash sigma dash, time order version of this you want to calculate, and the vacuum expected value of this. By the same logic, I can write this as theta t tau minus tau dash into x tau sigma x tau dash sigma dash plus theta tau dash minus tau into x of tau dash sigma dash into x tau sigma. So I can again take the derivative on both sides. Suppose I call this as delta x of tau sigma tau dash sigma dash. Suppose I call this is the propagator of the string. Actually this means this is abbreviated or shorthand notation for the situation when x is replaced by x mu and x here is replaced by x nu. If I calculate del by del tau of both sides, then I will differentiate this this theta function, this heaviside step function will become a delta function, you will get a delta function, negative delta function. So you will get a commutator between these two, which is 0 because both are position fields, an equal time commutator. But if we differentiate again with respect to tau, so I calculate dou square by dou tau square, then you will have to differentiate this quantity with respect to tau inside. So see what is happening is that if I differentiate this with respect to tau, I will get a delta tau minus tau dash here and minus delta tau minus tau dash. So you will get a commutator, equal time commutator between two position field which is 0. But if I hold this fixed and differentiate this, what will I get? That will give a non-zero contribution, right. So you will get simply, if you differentiate with respect to tau, I will get the time ordered version of dou tau of x multiplied by x dash. X dash means x evaluated at tau dash sigma dash. Again if I differentiate with respect to tau, then what will happen? So I will write this as T dou tau of x tau sigma multiplied by x of tau dash sigma dash. If I differentiate with respect to tau, if I differentiate again with respect to tau, what will happen? I write this as theta tau minus tau dash multiplied by dou tau of x tau sigma into x tau dash sigma dash plus theta tau dash minus tau times x tau dash sigma dash multiplied by dou tau x tau sigma. So if I differentiate this with respect to tau, I get a delta function here. Here I will get a minus delta function and you will get a commutator. So this will become a commutator between the momentum and the position and the momentum at the same time. That will give you a factor of delta sigma minus sigma dash. If I differentiate this portion with respect to tau, then holding the delta function fixed, then I get dou tau square of this. And if I differentiate the propagator with respect to sigma square, sigma twice, I will get dou sigma square. So what I will get essentially is that dou tau square minus dou sigma square acting on delta x tau sigma tau dash sigma dash will simply be equal to delta tau minus tau dash times the commutator between dou tau x tau at sigma and dou and x at tau dash sigma dash tau sigma dash, because there is a delta function already, plus I will get a term like the time ordered version of dou tau square minus dou sigma square. Dou sigma square will not act on the delta on the theta function outside, because the theta function is only a time ordering function, it is a function of the times, 2 times. So I will get dou tau square minus dou sigma square acting on x tau sigma multiplied by x tau dash sigma dash, and this quantity is 0 because the wave operator acting on x tau sigma is 0 by the equations of motion. So I get just this, and this commutator is nothing but delta sigma minus sigma dash. So this is nothing but delta tau minus tau dash delta sigma minus sigma dash. That means, in other words, the string propagator satisfies the equation dou tau square minus dou sigma square delta x tau sigma tau dash sigma dash is equal to a constant times delta tau minus tau dash delta sigma minus sigma dash. So if I replace sigma by I sigma, a complex variable, then I get that this is the Green's function for the 2-dimensional Laplacian operator. That means the propagator of the string is the Green's function for the 2-dimensional Laplacian operator, and you know that is equal to log of root of tau minus tau dash square plus sigma minus sigma minus sigma dash square. After you, if you put a Laplacian operator, it will be plus. If you change sigma to I sigma, you will get a minus here. So this is the string propagator. So now you can calculate the correlations using the string propagator. So if in summary, what happens? You have the vacuum expected value of x mu of tau sigma multiplied by x nu of tau dash sigma dash. This is equal to eta mu nu k times eta mu nu times log of square root of tau minus tau dash square plus sigma minus sigma dash square. Now you compute the energy momentum correlations. You saw that you could write it as T at say I denote tau sigma as sigma, okay, a single variable, vector variable, and T plus plus at sigma dash, and you compute the vacuum expected value, that will come out to be dou plus x sigma dou plus x sigma dash, and then you are taking the square of this vacuum, the time ordered version of this vacuum expected value square, which is nothing but you are differentiating dou plus square, you are differentiating twice the string propagator t of time ordered version of x sigma with x sigma dash, and then you are squaring the whole thing, but you know that the propagator is log of this, right. So, you can see if you take a left moving string for example, then x sigma into x sigma dash, the time ordered version of this for the left moving string is simply equal to sigma plus ln sigma plus minus sigma plus dash, and if you take dou plus you get, if you take dou plus of this quantity what do you get, if you take dou plus square you get 1 upon sigma plus minus sigma plus dash square, and then you square the whole thing. So, you get 1 by sigma plus minus sigma plus dash power 4. So, in other words you are, if you look at delta of the energy momentum tensor tau sigma tau dash sigma dash, this sort of a propagator, and you compute it as t plus plus tau sigma multiplied by t plus plus of tau dash sigma dash. If you look at this and you compute if you compute this, you get simply some constant k divided by sigma plus minus sigma plus dash square. Into anything else, there will be a delta function of time, delta tau minus tau dash. Just check that. See, if you calculate dou minus, so you calculate you write it down this way, t plus plus of sigma into t plus plus of sigma dash, time ordered version vacuum expected value of this is equal to so you have dou plus square of x sigma dash, time ordered version of this, it will be dou plus at the equal there will be a factor of delta tau minus tau dash, you can see that very easily. Actually what will happen is that if you compute this directly you will get dou plus dash, which is dou plus of that, okay. So, you will get a product of two such terms, and this is log, okay. So, this is nothing but log of sigma plus minus sigma plus dash, and you are taking dou plus square of this. So, when you take dou plus square, first when you take a dou plus you will get 1 by sigma plus minus sigma plus dash, and then you take a dou plus square you will get a square here, right. So, it is correct, that will not be a delta function, you will get simply that your delta t of tau sigma tau dash sigma dash is equal to a constant times sigma plus minus sigma plus dash square for minus 4. And you, on the other hand, if you calculate delta t of tau sigma tau dash sigma dash, this will be nothing but if you this is nothing but, okay, you can write it in this way, you can write it as theta tau minus tau dash into t plus plus of let us put sigma, denoted by sigma and sigma dash, the vector variable. So, t plus sigma sigma dash plus theta of tau dash minus tau into t plus plus of sigma dash t plus plus of sigma. So, if you use the string equations of the energy momentum conservation, I mean dou minus of t plus plus is 0, and if I differentiate both sides with respect to dou minus, what do I get? I get dou minus of this delta t is simply equal to a delta function here, a negative delta, it will give you a commutator, dou minus of this becomes 0. So, this becomes simply delta tau minus tau dash times the commutator between t plus plus at sigma, equal time commutators, and T plus plus at sigma dash, right, it becomes this quantity. And so what you can say is that if I take dou minus on both sides, I can equate this. So I can say that dou minus of this quantity, I can say that dou minus of sigma plus minus sigma plus dash power minus 4 is simply equal to delta tau minus tau dash times the vacuum expected value of the commutator T plus plus between tau and sigma, this into this, comma T plus plus into tau sigma dash into delta tau minus tau dash. But if you, so this will give you the anomaly in the commutation, in the Virasoro commutation relations. So if I now substitute, I can say that this is a constant times this. So if I look at sigma plus minus sigma plus dash power minus 4, that can be written as a constant times dou plus cube acting on sigma plus minus sigma plus dash power minus 1 into a constant. So I am taking dou minus of this, I am taking dou minus of this, dou minus, interchange dou plus and dou minus. So you get dou plus cube into dou minus acting on sigma plus minus sigma plus dash inverse. So what I get is that finally I get that T plus plus at sigma comma T, so T plus plus at T plus plus at tau sigma comma T plus plus at tau sigma dash, this commutator, into delta tau minus tau dash. Delta tau minus tau dash is equal to a constant times dou plus cube into dou minus acting on sigma plus minus sigma plus dash inverse. Now this sigma plus sigma plus dash plus sigma plus dash inverse can be written as simply dou plus of log of sigma plus minus sigma plus dash, and you are applying and this by dou minus dou plus, which is the wave operator, and you already know that this is the Green's function for the wave operator. So this can be replaced by a delta function of this can be replaced by a 2-dimensional delta function, namely delta of tau minus tau dash into delta of sigma plus minus sigma plus dash. So this quantity becomes simply k times delta of tau minus tau dash into a triple derivative of a delta function sigma plus minus sigma plus dash. So if I equate this, if I cancel out the delta function in time, I get the anomaly relation directly from here. It says that T plus plus of tau sigma comma T plus plus of tau sigma dash is equal to a constant times a triple derivative at sigma plus minus sigma plus dash, and this is the anomaly. This is a Virasoro anomaly. If you translate to the Fourier domain, what happens? This becomes simply T plus plus of of course the equal time commutation relations tell you this, and of course it also tells you that if you calculate the T plus plus sigma tau sigma multiplied by T plus plus tau dash sigma dash, take a time ordered version of this and you take dou minus of this, then that is equal to k times we are calculating this, okay. So it is delta tau minus tau dash into triple derivative of this at sigma plus minus sigma plus dash, right. So this gives you the correlations, the equations for the correlations. So if you look at the whole thing from viewpoint of Virasoro series, Virasoro Fourier series, that is you expand T plus plus as a Fourier series, T plus plus of tau sigma you expect as summation ln e power I n tau minus sigma or tau plus sigma, whichever, whether it is a right mover or a left mover, and substitute this into this relation, I will get ln comma lm, this is for the ghost field, will be equal to a triple derivative, means in the Fourier series domain you multiply it by n cube, okay, and you will have a delta n plus m term coming here for the ghost field. Likewise for the bosonic field you will have additional terms. So the two Virasoro anomalies, this is the only anomalous part, not the normal part, the anomalous part, because you are taking the vacuum expected value of this quantity, of this commutator. That is the anomalous part, you can say this is the anomalous part of the commutation relations, and the two anomalies between the ghost anomaly and the Virasoro anomaly, they cancel out precisely when D is 26. So I will come to that much later. Now what happens is that I can write this relation in the momentum domain. Whenever I have a dou minus, it amounts in the momentum domain multiplying by p minus. When I have a triple delta plus and sigma plus, this amounts to multiplying by in the momentum domain by p plus cube. So I can write this relation in a convenient form, namely p minus acting on the time on the correlation t plus plus at p into t plus plus at p minus acting on how should I write this? I should write this as so okay, you can look at it this way. You can look at it that from the viewpoint the Fourier transform of t plus plus at sigma and t plus plus at sigma dash. The Fourier transform of this with respect to I p into sigma plus minus sigma plus dash d sigma plus, this quantity, this is equal to k times a triple derivative will give you p plus cube here, and you take dou minus of this. So you have to divide by p minus, because dou minus of this quantity is equal to that anomaly. So you can also express this in this way, it is a convenient way of expressing the whole thing. The same as saying that you can put it in this form. You can say that in the Fourier domain t plus plus p, this quantity multiplied by p minus is equal to p plus cube into k. The anomaly could be expressed in this form. Now what happens when the field interacts with gravity? When the field interacts with gravity, namely the world sheet metric, so the metric is given by h alpha beta. So h alpha beta, t alpha beta is the interaction energy, which since only t, if I look at left movers alone, then this can be written as t plus plus into f plus plus d2 sigma, where f plus plus is the perturbation in the world sheet metric in h alpha beta, that is it is the perturbation in h plus plus. So now if I want to calculate the average value of t plus plus, the average value of the energy momentum tensor, I want to calculate this quantity, quantum average value, and then I want to calculate dou minus of this and show that this is not conserved. That is, in the classical case we had just seen that when classical field equations hold good, then this is 0, energy momentum is conserved. In the quantum case this will come out to be non-zero. So how do you calculate t plus plus sigma, the quantum average of this? You calculate it as simply e power I times the interaction Lagrangian, which is integral t plus plus sigma dash into f plus plus sigma dash d2 sigma dash multiplied by t plus plus sigma, and then you take the path integral. Let us say you are doing it for a bosonic string, so you take a path integral over all dx. So if you expand this e power I times this quantity, or you write it as, of course, into e power I times the original bosonic Lagrangian I s naught x. So if you expand, if the metric tensor perturbations are small, then I can write this as e power I s naught x into 1 plus I times this. So the extra term which comes out is t plus plus sigma dash into f plus plus sigma dash 1 plus I times the numerator, integral of this multiplied by t plus plus sigma here, and then you take dx, and of course you are also integrating this with respect to sigma dash. So integral d2 sigma dash. So you take, so this amounts to taking the quantum expected value of this quantity of the correlations, the quantum expected value of the product of t plus plus at two different space time points sigma and sigma dash, multiplying it by the metric perturbation and integrating over sigma dash. Quantum expectation value is being taken because you are multiplying it by e power I times the action and taking a path integral. So what you can say in conclusion is that the average value of t plus plus sigma is given by integral f plus plus sigma dash into average value of t plus plus sigma t plus plus at sigma dash d2 sigma dash. And we have seen that this quantity is non-zero. We have already just seen that dou minus of t plus plus of sigma into t plus plus of sigma dash, this is equal to a constant times a triple delta function. A triple delta function at sigma plus minus sigma plus dash. We will just see in this equation to hold good. So, how did we get this? We computed in terms of okay, there was a delta tau also in this or not, I do not remember. I think there was a delta tau minus tau dash also in this expression. So, there was a delta tau minus tau dash. That is because when you compute when you compute it using Wick's theorem, you get a product of pairs. So, when you get a product of pairs, you get dou plus x, dou plus x dash, like this you get. So, you get product of such terms, and each term is nothing but dou plus. So, you get dou plus square acting on ln sigma plus minus sigma plus dash, and then you are taking the cube of this whole thing. So, it is 1 by sigma plus power 4 that will come out. So, I do not think you will have a delta function here, right. It will be simply delta triple delta cube of t. Okay, you are taking the, if you take the equal time commutation relation, just check this. Okay. So, what happens is that this whole equation, anomaly equation, can be written in the convenient form as p minus, let me just go back and see. Okay. So, p minus acting on p plus plus p t plus plus p is equal to p plus cube into a constant, and you have also seen that the average value of t plus plus at p, t plus plus at sigma is given by integral f plus plus of sigma dash into the correlation t plus plus of sigma into t plus plus of sigma dash, time ordered version of this d2 sigma dash, which is nothing but, if you take the Fourier transform, this becomes t plus plus of p, average value of this becomes simply the Fourier transform of this evaluated at p multiplied the Fourier transform of this correlation. The Fourier transform of this correlation is given by p plus k p plus cube by p minus. So, you get a non-local term here, right. So, you see that energy momentum is not conserved, but what it gives a worse feature, that the average value of the energy momentum tensor is given by this, which is which contains a non-local term which diverges when p minus becomes 0. So, it cannot be removed, this anomaly in the average value of the energy momentum tensor not being considered. Of course, it comes out to be like it contains non-local terms, right. T plus plus p contains non-local terms. So, you cannot add counter terms to the Lagrangian to cancel out this quantity, right. There is no way by adding counter terms that you can cancel out this quantity. So, we see that everything is related, but what happens is that here you are taking the energy momentum tensor to be the total energy momentum tensor of the field, of the bosonic field and the ghost fields. But in the case, you can cancel it out in a particular case, that is, if you take a fermionic superstring. I think I will come to fermionic superstrings much later on, but what happens is, if you take the Lagrangian of a fermionic superstring, this plus right movers plus left movers d2 sigma, and you calculate its energy momentum tensor, then it will have both t plus plus terms and t minus minus terms. It will have both, but t plus minus will become 0 again at the classical level. But what happens is that again you get an anomaly when you couple this to gravitation, but you can cancel out this anomaly, because what is the energy momentum conservation read now? It will read dou t plus 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 dou plus t minus plus is 0, right. This is how the energy momentum conservation will read, dou minus of t plus minus plus dou plus of t minus minus is 0 at the classical level. T plus minus will not be 0 here in this case also. In this case, it will no longer be 0. You can add counter terms to make this 0. This will t plus minus will be 0 at the classical level, but you can add counter terms here to t minus plus, which are local counter terms to make this 0. because of this particular situation, and T plus minus will then involve, okay, what is T minus of in the average sense, when I say that is in the sense of averages, you can make this 0. In the quantum case, in the bosonics case, you saw that this was nothing but k times p plus q by p minus. So you could not add counter terms to this to make it 0, but when you have both a t plus plus and a t minus plus, you can introduce an artificial t minus plus term which is local, and so that this energy momentum relation is satisfied. But what happens is that this t minus plus will involve the metric perturbations f plus plus, f plus minus and f minus plus. So it will acquire a non-vanishing trace part. That means when you have t minus plus as non-zero, it will have a non-vanishing trace part, and you can compute this t minus plus very easily. T plus minus can be computed in terms of the Ricci tensor. It will come out to be equal to some constant times k naught times the curvature tensor of the manifold of H alpha beta of the metric H, world sheet metric. So it will no longer be traceless at the quantum level, although at the classical level we saw it was traceless, right. So scale invariance is broken. Now how to restore scale invariance? Either you can if you see what this t plus minus is, it will involve the anomalies. It will involve the anomaly coefficient, namely the commutator, the anomalous part of the commutator between the energy momentum tensor at the same times. It will involve such terms. So if you make those anomalous terms 0, which will happen when d equal to 26 and a equal to 1, you can cancel out those anomalous terms, in which case this will also become 0, this will also cancel out. That is, if the anomaly in the Virasoro commutation relations cancels out, then all the anomalies are restored, namely energy momentum tensor is conserved at the quantum level, and at the same time it is the energy momentum tensor is traceless at the quantum level. Both these issues are automatically satisfied. So next time I will talk about a fermionic string and what is the, how do you define the fermionic anti-commutation relations between the creation and annihilation operators of the fermions, and then how do you show that if you add the bosonic Lagrangian for the bosonic string Lagrangian to the fermionic string Lagrangian, and you define a supersymmetry transformation between the bosonic fields and the fermionic fields, then this total Lagrangian remains invariant and under global supersymmetry. If you want local supersymmetry, you must add other terms to it, and you must make the assumption that the dimension of the string is fixed, namely it comes out to be 10. So 10 becomes the crucial dimension of the bosonic plus fermionic string when they are coupled together. Okay, that is all I have to say. Thank you.